Yeah, so should I just start now?
Yeah, sure.
Okay, so yeah, thanks Karina for inviting me to give this talk. Today, I just want to talk about the Obel Jacobi Theorem. And I mainly just want to talk about some history of the theorem. It's a really nice story, and I just wanted to share it. So I wanted to begin by talking about what the theorem is roughly. So let X here be a compact Riemann surface. So this you can just take to mean a compact complex manifold of dimension 1. So if you're not familiar with these Riemann surfaces, you can think about this complex projective space, CP1, which can be thought of, at least topologically, as the one-point compactification of the complex numbers. So we also have this C mod gamma. It's another example of a compact Riemann surface. So you take the complex plane here, and gamma is this lattice inside of the plane. So it's these blue kind of integer points here. So this group will act on the vector space C. And if you take the quotient, you'll see that this segment here in green gets identified with this segment here. And this segment here gets identified with this segment up here. So with this identification, the C mod gamma becomes a torus. So this thing here is homeomorphic to a torus. So now I want to briefly say kind of what the Abel Jacobi theorem says. So given a compact Riemann surface, there's two natural complex tori, which are generalizations of the C mod gamma. So with some vector space, complex vector space of dimension G, modulo some subgroup. And again, similarly to this guy, it's homeomorphic to S1 to the 2G. And the two natural complex tori that are associated to this Riemann surface are the Picard variety, which is denoted by Pig0 of X, and the Jacobian variety, which is denoted by Jac of X. So the whole talk basically will be kind of aiming for the precise or more precise definitions of what these varieties are, what these tori are. And the Abel Jacobi theorem says that these two complex tori are the same. So there's some natural isomorphism between this Picard variety and this Jacobian variety. So that's roughly what the Abel Jacobi theorem says. And I just wanted to make some remarks for why this theorem is important. So obviously this theorem is useful in the study of algebraic curves. And it's been used a lot there. But I want to mainly highlight some other ways in which this theorem is important. So Griffith, who is one of the most famous mathematicians of the 20th century, said that the Abel Jacobi theorem is the beginning of Hodge theory. And I'll try to come back to this statement a little bit at the end of the talk to make it a little bit more precise. But Griffith is a Hodge theorist, and in his view, the Abel Jacobi theorem is kind of the beginning of the subject. And the other remark I wanted to make about the importance of the theorem is that trying to understand generalizations of this Picard variety leads to Grothendieck's construction of the Hilbert scheme. So I won't say what the Hilbert scheme is, but it's a really revolutionary construction introduced by Grothendieck. So the Abel Jacobi theorem maybe is less useful or less interesting as like the statement itself, but it's inspired a lot of really, really great mathematics. And hopefully we'll be able to talk a little bit more about that at the end of the talk. So before I get started on the history, are there any questions?
Yeah, sorry.
Yeah.
The complex tori are the same in which sense?
So there's going to be a canonical isomorphism between the two tori.
An isomorphism is a polynomial equation?
Right. So yeah,
Okay.
so an isomorphism of algebraic variety, because these complex tori are actually going to be algebraic, but I won't mention that at all. But you can just take it to mean like an isomorphism of complex manifolds if you want. Okay, so with that out of the way, I want to begin talking about some of the history of the theorem. So we start in 1694, and James Bernoulli is studying this Lemniscate equation. So I can't pronounce it, but the equation is given right here. So it's x squared plus y squared squared is equal to a squared times x squared minus y squared. And because I can't pronounce it, and this graph or the solution set has a really nice picture, I'll just call this like the figure 8 equation. So we have this nice figure 8 here. So he was studying this equation, and in polar coordinates, we can rewrite this equation as follows. So I have r squared is equal to a squared cosine of 2 theta. And Bernoulli was studying kind of like the arc length of this equation. So he computed that the arc length of this equation, which I'll denote by S, is equal to the integral from 0 to r prime, a squared over square root a to the 4th minus r to the 4th dr. So there's no exact formula for the arc length. It's one of these functions which is defined as an integral. So I want to make some remarks about this equation here. So the first is that S of r prime is not expressible as a sum of elementary functions. So we can't write it as, logs or exponentials or polynomials or any combinations of such objects. And the second remark I wanted to make is that this S of r prime kind of has a name, and it's a type of elliptic integral. So what does this mean? It means it's an integral of the form integral r of xy, r f of x dx, where r is a rational function and f of x is a polynomial of degree 3 or 4. So, right. So these types of integrals came up in the study of like elliptic orbits, and that's why they get this name, elliptic integral. Okay, so then we move to 1714, and Fagnano shows that he's studying these elliptic integrals, and in particular, this figure 8, the arc length of this figure 8 equation has a really nice property. He shows that 2 times the integral from 0 to a of dx over square root 1 minus x to the 4 is equal to the integral from 0 to b dx square root 1 minus x to the 4, where b has this nice form, or maybe not so nice form, but it has an explicit form, which is 2a times this expression. So what is this thing saying? It's saying 2 times this integral can be written in terms of another integral of the same form. So I want to make a remark that this result is surprising. It's not true for any arbitrary integral that you write down. So we can take this integral, 2 times the integral 0, 1 dx over 1 plus x squared. And hopefully, if I did this right, we should get 2 times arctan of 1, which is pi halved, which does not equal the integral from 0 to b dx 1 plus x squared for any b in the real numbers. So for these, for this arc length integral here, there's a really special property that's being satisfied, where 2 times it can be written in this way. So then in 1759, Euler comes along and he shows a big generalization of Fagnano's result. He shows that the integral from 0 to a dx over this square root 1 minus x to the 4 plus the integral from 0 to b dx over square root 1 minus x to the 4 is equal to the integral from 0 to c dx over square root 1 minus x to the 4. And c this time has the formula given here. So the remark is that we can recover Fagnano's result when a is equal to b. So this addition theorem is a big generalization of Fagnano's result. So Euler was studying these elliptic integrals and he stumbled across this identity, but he could not show a similar result when the degree of the denominator is greater than or equal to 5. So here inside of this square root, I have a polynomial of degree 4, and Euler could not generalize this result when the polynomial inside of here was higher degree. So we'll see in a little bit that this isn't because Euler just couldn't do it, but there's no formula that looks like this when the degree of the denominator is larger than 4 or larger than 5. So this, for a long time, was the most general type of addition formula for these elliptic integrals. And then in 1826, Abel comes along and he generalizes this result even further. And it's a huge increase in the level of generality in which the addition theorem holds. So he proves an addition theorem for something called an Abelian integral nowadays. So I don't know what they called it back then, but nowadays it's called an Abelian integral. So what is an Abelian integral? Let me make this definition. So it's an integral of the form psi of z, which is the integral from some fixed point z0 to z of a rational function of two variables, where x is a complex variable. So we've extended the domain for our integration. We're no longer just allowing real variables, but complex variables. R is a rational function. So similarly for the elliptic integral case. And importantly, probably most importantly, is that y is an implicit function defined by the equation f of xy is y to the n plus f1 of xy plus fn of x equals 0, where the fi's are polynomials.
So is that like y to the n minus 1?
Yeah, maybe I had the wrong indexing, yeah. So this
Oh, sorry, I meant the coefficient on the f1 function.
Sorry, f to the n minus 1 here. Is this what you meant?
No, so I mean you have y to the n, and then you go down to y, and then what are the remaining terms?
Yeah, sorry. Thank you. Yes, totally. Yeah. So basically, I have a polynomial in two variables. Thank you. So I want to make the following remark, is that there's an ambiguity coming from the path of integration. So z0 and z we think of as complex numbers here. And if I'm doing such an integral, I need to pick a path from z0 to z. And this integral is kind of ambiguous up to a choice of path. So I don't want to talk too much about this right now, but we'll spend a little bit more time talking about this later. I just wanted to bring this to your attention. So the definition maybe is kind of confusing, but let me just do a quick example of what an Abelian integral is. So for my function f, I take y squared plus x to the 4 minus 1. And therefore, if I'm looking at this 0 locus, kind of one of the implicitly defined functions is y equals square root 1 minus x to the 4. And then my rational function is 1 over y. So then my Abelian integral is something that we've seen before. It's this arc length integral that we considered at the beginning, this figure 8, the arc length of the figure 8. So with this definition, I wanted to make the following remark, which is that algebraic geometry kind of begins to enter the picture. In that we're looking at the 0 locus of a polynomial equation in two variables. So this, by definition, is the set of all pairs x and y in C squared, satisfying f of xy is equal to 0. And I'll probably call this C throughout the talk, this 0 locus. So by definition, C is an affine algebraic variety. And in particular, it's a curve. So it's a affine algebraic variety of dimension 1. So I think in Lisa's talk, she mentioned such a thing. Okay. So now that we've talked about these abelian integrals, we can talk about Abel's generalization of Euler's addition theorem. So Abel's generalization is the following. So he takes any abelian integral, psi of z. So you can take the previous one as the example. And then he fixes rational numbers a1 up through a alpha. So some collection of rational numbers. And then he shows there exists a positive integer g such that the following expression holds. a1 psi to the 1 x1 plus a alpha psi to the x alpha is equal to v, which I'll define in just 1 second, x1 prime plus psi xg prime. So there's a lot going on in the notation of this theorem. Let me try to break it down. So here we think of the xi's are independent complex variables. And v is an elementary function in the variables x1 through x alpha. And then these xi primes are algebraic functions of x1 through x alpha. And these xi primes work for every abelian integral psi. So there's, given some independent variables x1 through x alpha, I can find these new variables x1 prime, xg prime for that satisfy such an equation for every abelian integral. And the last statement here is that g is the minimal such positive integer. So I won't say too much about what minimal means precisely, but kind of there's no smaller number of variables on the right-hand side for which such an expression is true. So let me pause here for a second and see if there's any questions about the notation that maybe I didn't explain well enough.
So each xi prime depends on maybe all the xi's?
Yes, correct. So I have my initial variables x1 up through x alpha, and I can write these xi primes in terms of those.
So
kind of like a
is
change of
G,
variables.
so does G just depend on alpha essentially?
Right. So I think we'll see later that G actually right. So G, I think, depends more on the abelian integral than on the x alphas.
It's like you have a sequence of x primes, and how many of them you need depends on.
Yeah.
on
Yeah.
C,
So yeah,
right?
I think there is some dependence. Yeah.
Oh, sorry, can you clarify that this works for every abelian integral?
Right.
You mean that you're choosing
Right. Sorry.
a
So
priori
right. So I said something wrong. So you have to choose a number alpha, as Med said, and then you can form these x1 primes or xi primes. And if you look at any kind of abelian integral, you can write down such an expression. So the same choice of these xi through xi prime, x1 prime up through xg prime work for different choices of psi.
Okay.
So I said something wrong.
Thank you.
Okay, are there any other questions? So the statement is a little bit difficult to parse, but we're not going to really use it, but hopefully it just convinces you that at least it's a generalization of the stuff that we've been talking about previously. Okay, so let me just do the quick example of what we talked about previously. So if I let this be the integral from z0 to z of this dx square root 1 minus x to the 4, the Euler's addition theorem said that psi of A plus psi of B is equal to psi of C, where C is equal to A square root 1 minus B to the 4 plus B square root 1 minus A to the 4 over 1 plus A squared B squared. So here my xi's are A and B. My elementary function v is equal to 0, so I don't have a contribution right here. And I only have one xi prime, which is c, and it's given by this function over here. So this is a special case, or this addition theorem is a special case of this Abel addition theorem. Okay, so in the remainder of the talk, we're going to focus on the special case of hyperelliptic integrals. So here we're going to take the equation f of xy to be y squared minus phi of x, where phi of x is square-free polynomial of degree d. So in particular, it means no multiple roots. So just to remind you guys, this f of xy is the thing that's appearing in the definition of this abelian integral. So for these hyperelliptic integrals, Abel computed that g, this number, is equal to d minus 1 over 2, where again d is the degree of the square-free polynomial when d is odd, and it's equal to d minus 2 over 2 when d is even. So in particular, g is equal to 1 when d is equal to 3 or 4. So this is kind of the case that we have here. So they have a degree 4 polynomial inside of this square root. And here, g is greater than or equal to 2 when d is greater than or equal to 5. So I wanted to make a couple of remarks about this. And the first is that g, we'll see in just a little bit, is the genus of the Riemann surface associated to the equation f of xy equal to 0. So I have this polynomial in two variables. It defines for me some affine algebraic variety inside of C2, which is dimension 1. And from some way, I can cook up a Riemann surface from that. And we'll talk about that in just a little bit. And this number g that Aval is coming across is the genus of such a Riemann surface. And the second remark that I wanted to make is that Euler is justified in not being able to generalize his addition theorem. So what do I mean by this? I mean, you can't write something like 0 to a dx square root 1 minus x to the 5 plus integral 0 to b dx square root 1 minus x to the 5 as some integral from 0 to c dx square root 1 minus x to the 5. You're going to need at least two things on the right-hand side.
Can I
Yeah.
mention something?
Yeah.
So it seems here, and this is just surprising to me, that G appears to not depend on alpha. So I could have multiple, like I could change alpha, but G is going to be the same.
Right. So So I definitely have said a lot of wrong things about this addition theorem here. So I think I would need to think a little bit more about the precise statement. So let me cross this one off right here. Let's pretend like I didn't make that statement. But yeah, it is I guess a little bit surprising that it doesn't depend on alpha from this perspective. We'll see a little bit more later on when you formulate things in the modern language. It's a little bit more clear what's happening. So let's hopefully just put this to a side for right now and come back to it in just a little bit. So that's a really good observation. Is there anything else?
That's it.
Okay, so Abel came up with this addition theorem, and he asked the following question, and this question is going to be the one that kind of leads to the Obel Jacobi theorem. So he asked, when is the sum psi of x1 plus psi of x alpha constant? So I have all of these, I have this Abelian integral psi, and I can think now about the xi as points on C equals C of f. So it's a little bit confusing, but now I'm thinking of these independent complex variables as moving around, as points which are moving around on my curve. And I'm asking, when is this integral here constant? So the answer here uses the following definition. And the definition is an Abelian integral psi is of the first kind if the integral is everywhere finite. So if I have a bounded integral, then it's of the first kind. So let me do the following example in the hyperelliptic case. So just to remind you, I'm looking at an equation f of xy with y squared is equal to phi of x. This is some square-free polynomial of degree b. And this gives me the equation, if you take differentials and stuff, dx over y is equal to 2 dy over phi prime of x. So when I have some point on the curve, like or I guess the important thing here is that this integral makes sense even when y is equal to 0. So a priori, we could have some poles when y is equal to 0. But because this polynomial is square free, it has no multiple roots. So for the points here that make the points that lie on the curve with y equals 0, this right-hand side is actually going to be something that you can integrate. So an explicit example here would be integrals of the form integral z0 to z dx over square root phi of x. And then I have integral c z0 x to the g minus 1 square root phi of x are examples of integrals of the first kind. So these integrals will be everywhere finite. So this is the first thing we need to answer Abel's question. And the second thing we need is this notion of equivalent points on the curve C. So I can take any alpha collection of points, x1 up through x alpha, and I'm going to take a different collection of alpha points, x1 prime to x alpha prime. And I'm going to say that they're equivalent if after I remove all of the common points in both collections, the remaining points are the zeros and poles of a meromorphic function. Let's see. So if you're familiar with algebraic geometry, this really is just linear equivalence of divisors. And we'll see that a little bit later on when we formulate this in more modern language. But for now, I just have some collection of points on C, and I'm defining the notion of equivalence. So the important theorem that Abel showed is Abel's equivalence theorem.
So,
Yeah?
Sorry, man. What prevents every collection of points from being equivalent to any other if they are finite?
Well, they have to be the zeros and poles of some meromorphic function on C.
Can you just make a rational function and prescribe those as the zeros and poles?
Yes, yes, but I don't know if you can do it for all of these collections of points. I don't think you can do it for all collections of points.
Okay.
Right.
Yeah,
I might say something here that I was thinking the same thing at first, because on the complex plane, I mean, you can do this for any set of points, but it's not clear to me how, like, and maybe it's not clear at all how restrictive it is to say that we're restricting to a Riemann surface C that's not necessarily the complex plane.
Right.
Ah, okay. So this is on the Riemann surface?
Yeah, this is not complex number C. This is the zero locus of my equation C.
Okay. Thank you.
Yeah.
And thanks, Tim.
Can I also ask, I'm kind of turning my algebraic geometry brain on here, but are you trying one collection to be the zeros and the other to be the poles? Or how do the signs
I'm
work
just
out?
not taking the signs really.
You're just
into
not
account.
even bothering with that? Okay.
I'm not talking about that just yet.
Okay. So it's just a random jumble of zeros and poles.
Yeah, exactly.
Okay.
Exactly. For right now. We'll become a little bit more precise in modern language in just a little bit. But the theorem that Abel proved is the Abel's equivalence theorem, which says that the sum psi of x1 plus psi of x alpha is equal to psi of x1 prime, psi of x alpha prime, if and only if these collections are equivalent. So there's some relationship between collections of points on this Riemann, I guess open Riemann surface for right now C, and these abelian integrals. So Abel actually only proved half of this theorem. So Abel proved the up direction, and the down direction is proved by Clutch in 1864. But together, they're known as Abel's equivalence theorem, even though Abel only had half. Okay, so now we'll start to enter the more modern perspective. And this is due to Riemann in 1857, when he introduces the notion of a Riemann surface. And he's going to provide a reinterpretation of this equivalence theorem. So let me be a little bit more precise on what I mean by the Riemann surface associated to this equation f of xy is equal to 0. So I'm just going to sketch it. And remember that C is equal to the 0 locus of this equation inside of C2. And it has a projection map pi from C onto one copy of C, which sums the pair x comma y to just x. And this map is holomorphic. And one can show that it's 2 to 1 and it's branched at several points. And the number of points at which is branched is related to the degree of the square-free polynomial phi. And then the theorems of Riemann show that this extends to a 2 to 1 branched cover C tilde of the complex projective line CP1. And this C tilde here is the Riemann surface associated to this equation. The C tilde is the associated Riemann surface. Okay, so I want to make a remark about these integrals of the first kind. And these integrals of the first kind are holomorphic differentials, or I guess integrals of holomorphic differentials on this associated Riemann surface. So these integrals of the first kind are related to stuff about the Riemann surface. And using this, we can now start to talk about the Jacobian, which is one of the complex tori that I mentioned at the beginning. So Riemann shows that integrals of the first kind form a G-dimensional vector space. And in our example of these hyperelliptic integrals, a basis of this vector space can actually be taken to be these integrals that I've written down here. So the integrals, which are finite everywhere, form a G-dimensional vector space. You can think about this as the holomorphic differentials on a Riemann surface of genus G form a G-dimensional vector space, complex vector space. And then he also shows that each integral of the first kind has 2g periods. So remember at the beginning when we talked about these Abelian integrals, there was some ambiguity that comes from a choice of path of integration. So Riemann shows that there are kind of 2g numbers kind of which generate all possible changes in the value of the integral which come from changes in the path of integration. And from this, he forms the period lattice gamma inside of this g-dimensional vector space. And the definition of the Jacobian is it's this vector space, which are the integrals of the first kind, where I've kind of picked a basis. And then I'm modding out by this period lattice. So I'm kind of getting rid of the ambiguity of changing my path of integration. So this is what the Jacobian is. And in modern language, it's a little bit easier to write down what it is. It's H0 C omega 1 C. So these are the holomorphic differentials on C. I have the dual vector space, which I can think of as integration along the forms. And I mod out by changes in path. If I have two different paths from connecting 2 points, they form a loop in my Riemann surface. And that's exactly kind of what this first homology captures here, or this fundamental group captures here. So this is kind of the more modern way of writing down the Jacobian. But when Riemann was doing it, he thought of it as integrals of the first kind modulo this period lattice. So this is what the Jacobian is. And with this new interpretation, Riemann formed something called the Obel Jacobi Map. And it's done as follows. So I fix a basis of my integrals of the first kind. We know it's a g-dimensional vector space. So I pick g integrals of the first kind. And then I look at the symmetric product of my Riemann surface. So the symmetric product is where you take the curve and you multiply it by itself alpha times. And then you divide out by the symmetric group action, which kind of permutes all of the factors. So this is the symmetric product. And Riemann forms the Abel Jacobi map, which sends x1 up through x alpha to the point I equals 1 to alpha, psi 1 of x1, xi, I equals 1 to alpha, psi g, xi. So we know that this thing here is parameterizing integrals of the first kind. So that's why the target of this is the Jacobian. So what is Abel's equivalence theorem saying? So Abel's equivalence theorem is saying that the fiber of this Abel Jacobi map consists of equivalent sets of points. So this theorem about when the sum of an abelian integrals, or when two sums of abelian integrals are equal, is in effect studying the fiber of the Abel Jacobi map. And it's saying that if you have equivalent collections of points, x1 up through x alpha on your curve, then they're kind of giving you the same number over here. So this is the reinterpretation of Abel's equivalence theorem. So maybe a little bit more precisely, we can phrase it as follows if we introduce the notion of the Picard variety. So let me give the definition here. So C now is my compact Riemann surface. And now we'll kind of more formally define what we mean by collections of points on the Riemann surface. So a divisor on the curve or the Riemann surface is just a formal sum of points, the sum ni pi, where pi are points in C. And the ni's are integers, positive or negative. So the degree of a divisor is just the sum of all of these coefficients. So maybe I should add here a finite formal sum. So this one here is always finite. So then we say such a divisor is principal if the divisor, if the points can kind of be written as the zeros and poles of a meromorphic function on the curve C. So the positive ones kind of correspond to the zeros, and the negative ones will correspond to the poles. So this is kind of the same type of thing that's appearing, the same notion of equivalence that's kind of appearing in Abel's equivalence theorem that we saw earlier. So now we can define a group, which is called the Picard group, which is the divisors modulo the principal divisors. And I wanted to write down the following fact that if I look at the divisors of degree 0, and I quotient out by the principal divisors of degree 0, I get the Picard group of degree 0. And this is a complex tori. So I don't want to go through the proof of this fact, but this divisors modulo principal divisors of degree 0 is a complex torus, and it's called the Picard variety. So now I wanted to make the following remark, is that the Obel Jacobi Theorem, or the Obel Jacobi Map, where alpha equals 1, gives a group homomorphism which I'll also denote by AJ, but it will go now from pick 0 of C to Jack C, and it sends a divisor of degree 0 to the sum like this. So given a point on the curve, I know what the, I have the Abel Jacobi map, which takes me into the Jacobian. So if I have a divisor, I kind of define this on points and then extend by linearity. So the Abel Jacobi map, which we first interpreted as this map from symmetric products of the curve, actually makes sense at the level of divisors, and in particular at the level of the Picard group. So we can now state the Abel Jacobi theorem as we gave at the beginning, and it says, oh sorry, maybe this should be div 0. So the Abel's equivalence theorem says that the kernel of the Abel Jacobi map is the principal divisors of degree 0. So therefore, we get an injection from the divisor, from the 6, 0 of my curve into Jack. Let's see. So this is the Abel part of the Abel Jacobi theorem. And I haven't mentioned Jacobi at all, but Jacobi shows that Abel Jacobi map is surjective. And this is what's giving us the identification between this Picard variety and this Jacobian variety. So I don't have much time left, so I just wanted to make one last remark, and it's about Griffith's comment at the end, or at the beginning. So Griffith's comment was about the Abel Jacobi map, or Abel Jacobi theorem. Is the foundation of Hodge theory. And his justification for this is that by looking at these integrals of the first kind, Abel is identifying the vector space H0 of C omega 1C. And this vector space is something that appears in the Hodge decomposition. This is like H10 of C appearing in the Hodge decomposition. So this tool and this subject that's really prevalent nowadays in algebraic geometry, in some sense can be traced all the way back to the 1600s in the study of these elliptic integrals. So I think I'm a little bit over, but I'll stop there.
Great. Thank you so much, Ben. That was a cool talk.
Yeah,
so are there any questions?
Can you say a little bit about Jacobi's contribution?
Right, I didn't actually look much at what Jacobi
I'm just wondering,
did.
Because
but,
in this classical setting, it seems like the Jacobian is basically generated by values of these integrals.
Right.
So I'm wondering what the non-trivial part of the statement is here.
Right. So I didn't fully understand what Jacobi was doing when I was reading this, but he was also looking at these integrals, these Abelian integrals. He's looking at this addition theorem, wherever it is. And he was asking like, which functions can have Abelian integrals like as the inverse or something like this. So it's something about some sort of inversion process of these Abelian integrals is what Jacobi was asking. And this is the thing that leads to the surjectivity of this Abel Jacobi map somehow. But I don't know the story very well.
Okay.
Yeah,
I'm wondering if it has to do with like restricting to degree 0 divisors, if that's what makes it difficult or something. I don't know.
Yeah, I'm not too sure, unfortunately. So sorry.
Great talk.
Yeah, thanks.
I'm wondering if you could say something about the path integrals. I mean, is there an easy way of saying what those look like or restrictions there are?
Right. So I don't know if I'll be able to say too much, but here, if I'm like working in a really, really small domain, like let's say simply connected domain, then if I have a point here, Z0, and a point here, Z, and I have one path of integration, like this, and I pick a different path of integration. The composition kind of going this way forms a loop. And if my domain is really small, like I'm working in a simply connected domain or I'm working in some disk, like all of these loops are kind of contractible. So it doesn't matter, in that sense, it doesn't matter which loop I'm taking. But if you're working on the entire Riemann surface, there's like non-trivial loops. And these non-trivial loops are gonna change the value of the integral. So when we said here that, wherever, there's like 2G periods, these are coming from the generators of the fundamental group of the Riemann surface. There's like 2G generators for the fundamental group of the Riemann surface, and these are kind of what's changing the value of the integral.
Okay, so the path is defined up to being contractible when you were to add like, you know, any two are equivalent if when combined together.
Right. If like the homotopy, it's like you can, you know, contract the loop from the homotopy or something. Yeah. So that's when two paths give you the same value for the integral.
Okay, but then this holds like whatever path I wanted. So like they give me different values if I go different ways, but this holds sort of for whichever path I choose is.
Right. Yeah. So like if you have let's say like the punctured disk or something, and you have a point here and you have a point here, and you go around this way, and then you go around this way, like the value of the integral might be different.
Right, but somehow
like non-trivial topology.
Either could be used in the setting of like the theorems that.
Yeah. That's the point, is that's the ambiguity of the definition that I gave, is I just said pick some path. It doesn't matter which one, but just some. And Riemann kind of solves this ambiguity by noting these using these periods. So that's what Riemann is doing here. If he's solving this ambiguity. Yeah.
Cool.
So I didn't explain that very well.
All right. Well, thank you again, Ben. And
Yep, no
yeah,
problem.
see everyone. So we'll end here.
Thanks, man.
Yeah, no problem.